design for Chapter 9. So first, we'll look into the constructions as well as the equivalent circuit for a phase of a generator. So from there, we can actually estimate what would be the fault currents, like short circuit currents magnitudes. And then based on the two major components that make up a machine, which is in this case the generators, we have stators and the rotor. So we'll see different kinds of faults that can be happens in the stators, such as the interturn fault. So interturn fault is actually due to the winding insulation failure within the same phase. We have short circuit conditions, as well as short circuit to ground occur as an earth fault situations. And then we also will see the unbalanced load condition. So now for unbalanced load condition, it will also cause the abnormal operation for a generator as well. So we'll see what are the available protection scheme we can apply to protect against these kinds of problems happen on the stators. Then we'll discuss about the rotor electrical fault as well. So typically for the rotor, it's the components we have in the generators has been wound by the fields winding to set up the magnetic fields. So you can see the problems like we have winding insulation failure as well, so short circuit to ground. So we have earth fault in the fields winding. And then we have loss of excitations can be seen as well. So we'll see what is the cause that result these problems and how to prevent them from occurring for our generators. And lastly, we also talk about the abnormal operating conditions that could be happens at the power plants, such as loss of prime mover. Prime mover is actually the components that give the motions to the generator. So right now it might be no longer working. So we have reverse power flows situations. And then we could also have loss of synchronism for the generators we have in the power plants. So this is due to the heavy disturbance we have in the power system. So we'll see how actually we can deal with this so that we can allow the generators that could be operated normally in the power plant. All right, so now the lesson learning outcome for Chapter 9, we have only two. The first one will be to identify the suitable protection scheme that can be applied for the generators based on the faults. And this fault can be further classified into both mechanically and electrically. Then it's time to do the analysis. So we will have calculation involved as well in Chapter 9. So we'll see how does the generator protection scheme being affected by the earth fault resistance we have been chosen. So here there are some calculations able to see how does the percentage of the status winding change with respect to earth fault resistance value we have been selected. All right, so now let's move to the first slide here. So on the introductions, talk about what is these components we have in the power system. So for generator is actually a very important component that you can find in an electrical power system. Why? Because it's played as the heart of the electrical power system. So it's performed its task by changing the mechanical form of input, which is the motions, and give us the electricity, which is the electrical power, as you can see by referring to the diagrams here. So for this generator is considered as the most expensive components you can find in the AC power plant. So same as other components we have in the system, so that might be fault occurs at the generator as well during its operation. So there's a need, so there's a demand for an extensive protection scheme being applied for the generator, which comprise a large variety of protective relays. So now let's check out these figures here. So this is the block diagram of the coal power plant. So this is a place where it generates the electricity. So this is where the generators can be found. So this generator actually looks like this is actually driven by a steam turbine. All right. So this generator has to be connected to the grid so that the electricity generated can be supplied to the consumer. So now the rotations of this steam turbine is actually given by the gas here through the burnings of fossil fuel. All right, so the fossil fuel here, so you burn, it will have the gas, give the rotations of this steam turbine. So that's how we have the motion, the mechanical motions. All right, so you also can see that there will be a cooling tower located nearby the power plants, where its intention to be used is to discharge the wasted steam to the atmosphere. Okay. So this is basically where we can find the generators in the power plant. So it's a very big components, all right, you can see. All right, so now let's move on to the next slide here. So we'll look into this diagram before we explain the contents we have in this slide. So this is actually a generator. The generator has been connected to multiple systems, including the prime mover, and then we have a DC field excitation circuit, and one more component that also being connected to the generator will be the power grid. So from here you can see the DC field source here will actually give the required reactive power from the grid to the generators. And this generator will supply both active power and reactive power to the power grids. So for this power grid is associated with stability issue. So we need to synchronize these generators with the power grids here. All right, and then this synchronism might be lost if, let's say, we have generators failure. So we have to take care of this generator. So now, what happens if we have fault occurs on the generators? So by disconnecting these generators, right, we will actually overload the rest of the system. So now we know that in the power plant, we could have more than one generator that is working there, right? So if you, instead of 3 now, you trip 1, becoming only 2 generators. Only 2 generators supply the entire system, which means that we have overload situations right now to the power system. All right, so at the same time, by tripping this generator itself is not enough. Let's say we have 40 generators. So unlike another components we have in the power system, by just open up the breakers to isolate the defective generators, now you can't have this generator just trip, then there will be no issue. All right, why? Because this generator has been connected to multiple system, right? So as long as the prime mover is there, right, it will give the motions. All right, so we need to treat this prime mover here by either stopping the fields, all right, supply the prime mover so it's no longer moving, and at the same time we should ensure also this DC field excitation circuit stop supplying fields so that it will give the required reactive power to the grid. So now we have to stop the motion and also remove the fields from this DC excitation source here. So that only we can fully isolate the defective generators out. All right. So as long as this two is moving, these generators, the faulty generators will still continue supply power to its own fault. Okay. So in such a case, the generator can actually damage the component in the downstream. All right. So furthermore, for larger size of machine, large machine, which means that it's able to generate much more higher power. So during the time, if we have fault, we also need to pump the carbon dioxide to it. So with such a case, we can extinguish any burnings of the insulations. All right. So whenever we have large size of machine, this indicates that if we have faults occurs, the fault current also very high as well. So this high current might be sufficient to generate high heat that causing it to burn the insulations. That's why we have to pump in the carbon dioxide. All right, so now let's talk about one of the systems that has been connected to the generators, which is the prime mover, the one that gives us the motions. So let's check out the first bullet point here in this slide. The prime mover is actually act as a source that give the mechanical input for the relative motions of the generators. Now, depending on the applications of the power plant, so steam turbines are exclusively used by the main power utility. So the main power plant, the motion is actually coming from the steam turbine. But in the industry, we can actually find 3 different types of prime mover. So the first one is actually same as the main power plant. We can also use steam turbine in the industry as well, whereby this is used whenever waste steam is available. So usually it will use as a baseload or as a standby. Okay, and then we can also use the gas turbine as well for the motions. So usually it's being used for peak looping or mobile applications. So this indicates that is the application with much smaller amount of power generations. And third one, we could have diesel engine as well, or you call it as a diesel power plant. So this diesel power plant is very popular, serve as a standby power plant for the main power generation stations. Okay, so usually the standby is coming from the diesel engines. All right, it also known as auxiliary power plants. All right, so now let's talk about the another system that also being connected with the generators, which is DC field excitation circuit. So there are actually two common ways to supply DC power to the field circuit on the rotating throttle. So one of it is by supplying the DC power from the external DC source to the rotor by the means of slip rings as well as the brushes. So let's check out this diagram here for better understanding how does the power is being supplied. All right, so now this diagram at the right-hand side is actually showing a three-phase alternators. Alternator is another name for the generators with this power rating 500 megawatt ampere operating at the voltage 12 kilowatts at 60 hertz frequency. All right, so this rotor is actually coupled with the main exciter at the left-hand side here. Okay, so these main exciters will actually produce the excited fields. All right, so the DC voltage will be generated at these main exciters. And this DC voltage will actually produce the current we call as the field current. So this field current will send into the rotor winding through the slip ring as well as the brushes. So in these examples here, the field current is feeding in at 6,000 ampere. All right, so it's actually flowing into this rotor winding that's being highlighted in blue. So whenever we have motions, the prime movers rotate, the voltage will induce we call it as the EMF, electromagnetic force, based on the Faraday's law. All right, so this voltage will induce in the stator. So the generated voltage will actually supply to the grid via the three-phase terminals here, A, B, C phase here. Okay, so this is the first way we supply the power, all right, to the rotating throttle. So now the other way is by supplying the DC field current to the rotating throttle by using the brushless exciters. So usually for this method will be applied for larger size of machines. So if you check out this diagram, right hand side again, we have the three-phase generators, and this time the generator has been connected to the main exciter, or we call it as the AC brushless exciters. It's actually a mix of a small generators. So this output from the generators will actually go through a three-phase bridge rectifier. So now the voltage will be rectified into the DC field current IX here and same fit into the rotor. All right. So basically, this is the another way of supplying the DC field current through the rotor winding, and this method will be used for larger size of machines that can be generating much more higher powers values. All right. So now let's see the equivalent circuit for a phase of a generators by looking into these diagrams. Okay. At the left-hand side here, we have the excited circuit. So now we know that excited circuit is being used to supply the current to the field winding. So this field winding will be wound around the rotor. All right, so now with the supplying voltage, VF here is the field voltage. It will cause IF, the field current flowing through the winding. All right, so whenever we have current flowing through the winding, it will generate the magnetic flux or magnetic fields. And then at the right-hand side, we have the status winding equivalent circuit. So based on the Faraday's law, you can notice that there will be voltage induced here, all right? So voltage induced in the status whenever we have rotor rotate, all right? Cut through the giant magnetic flux here. So based on Faraday's law, the voltage will actually induce. So for each phase of the stator winding, you notice that it consists of series connected stator resistor RA, we call it as an armature resistor or stator resistor, in series with the stator's inductors. All right. So here V phase is basically the output voltage generated by the generators where we connect it to the loads or to the power grid. IA here we call it as the armature current. Okay. So now let's see the other slide here. We will look into the components that make up a generators. So for a modern large generating unit is actually a complex system. It will consist of numbers of mechanical as well as electrical components, including the status winding. So stator winding will actually connect to the main and unit transformer that's typically found for larger size of generators. And then we have rotor as well. Rotor is the rotating parts of the machines. So it will actually wound by the field winding. So this field winding will be supplied by an exciters, as being explained in the previous slide. So in which its intention here is to generate the magnetic fields for the machine operations. And then we have mechanical components as well, like the turbine, whereby this turbine here will give the mechanical motions to the generator. So usually turbine will be installed nearby a boilers or the condenser that equipped with auxiliary fans as well as the pump. So right now, this boiler can give steam to the turbine blades. That's how it's rotate to have the motions. Okay, so this is electrical part. This is mechanical parts. All right. So now we will talk about the configuration for the generators that we can use in the power system networks. So now, depending on the size of the generators we have two kinds of connection or configurations for the generators. So one is known as direct connected configurations. Another one is unique connected generator system. So for direct connected system, right, is also known as bus connected system, typically with low impedance. So it's being configured for smaller or medium size of generator. So you can see the generator directly connect to bus. So that's why it's not as direct connected generator system. Okay, so now with this configuration, you likely found in the industry, commercial, as well as the isolated system. So basically, because directly connected to the bus bar, it has very simple connection. So it's inexpensive in terms of implementations, right? Because lesser components will be used. All right, so we have another one which is for bigger size of generators that are able to generate much higher power. Is known as unique connected generator system, which is with much higher impedance value. So now for larger capacities of generators, it will have its own dedicated transformer. So this is what we call as a unique transformer. This is what we call as the main transformer. So the generators will connect with the transformer before connect to the bus bar. In this case here, we have high voltage bus bar. So the generator's voltage will be stepped up before we transmit to the distribution side. All right, so you can see these connections, right, likely to be found in extra high voltage grid, such as the large utility system as well as the industry. Okay, so now you can see for both connections, right, the generators is neutral point will be connect with the ground, where certain impedance in between, like the earth resistance, so that we could have these generators being protected against earth fault situations as well. Let's say for the status winding. All right, so now let's move to the next slide here. So what are the major types of faults that you can find for the generator? So before we have this discussion for the protection scheme can be found for the generators. So for the fault itself, it can be broadly classified into two categories. One is known as electrical failures. Another one will be known as mechanical failure. So we will focus on mechanical failure first. All right, so whenever you see mechanical failure is linked to the rotations, it's not smooth or no rotations. All right, so under such situations, we could have the issue coming from the prime mover. So the prime mover might be not working, so there's no rotation, or probably we have the supply, all right, for the steam. We have a low condensers vacuum situations, or probably we have lubrications oil failures, or even the loss of boilers firing here, which means that the boiler is no longer working, no steam is being generated, so no gas, so no movements coming from the prime mover. So that is considered as the mechanical problems, all right? And not only no rotations, we could have overspeeding situations as well. So it's being turning too high, all right, the speed. So this overspeeding could be happen because we have sudden load removal at the distribution side. So much lesser loads to be supplied right now. That's why it's able to rotate much more faster. Or probably we have sudden increments in terms of input to the prime mover. So which means that the gas you supply right now, the volume is too much. That's why we have overspeeding situations. All All right, so whenever we have much higher speed for the machine, so it's actually linked with the voltage. High speed also linked to over voltage situation or over frequency situation. Is being turning too fast right now. So over voltage and over frequency is considered as the electrical fault for the generators. So right now, not only this, the generator stability is also concerned with the frequency operating limit as well. So overspeeding situation might cause the gyros being rotated at a non-intended speed limit, and hence it can cause the damage to the mechanical components such as the turbine blades can be damaged, the bearings, the gears and all. All right, so because of overspeeding situation, it can cause the components to be damaged as well. All right, so we have the mechanical failures. This is about the overspeeding situation. So not only this, we could have rotation might be distorted. We have vibration, excessive vibrations. This could consider as a mechanical fault as well for a generators. So this is for mechanical failure. So how about for electrical fault? So whenever we focus on electrical fault, so this fault can be happens on both stators as well as rotor. So we could have stator electrical fault and rotor electrical fault. Okay. So for stator failures, right, you might notice that we might have winding insulation failures for the stators. So this winding insulation failure can be happen between the phase. So we have phase-to-phase fault, or within the phase interturn fault, or even with the involvement of ground, we have short circuit to ground. This is because of the insulation failures. Okay, and another issue is coming from the overload situations. Then over voltage, which is linked to overspeeding situations, followed by unbalanced load situation. So whenever you see unbalanced, so we know that generator is a three-phase components, right? So it has three phases. So let's say each phase has been looked differently. It will actually leading the situations of unbalanced load conditions. All right, so we have to focus on this problem as well, how actually is affect the operation for the generators. That is for the stator fault. How about for rotor fault? So rotor, remember, is during the magnetic fields, right? So now we could have rotor failures due to loss of excitations, all right? Like over excitation. So now we could have the rotor problems. And this is the rotor problem. The last one here, right, is actually the abnormal operations for generators, whereby we has loss in terms of synchronism for the generators we have in the power plant. It become out of step. It's no longer work as 50 hertz or 60 hertz due to the disturbance we have coming from the power system networks. So these are all the possible problems that you can observe for generators that occurs electrically. All right, so now let's start to talk about the generators production scheme. Okay, so now we are focusing on overload productions. All right, so we'll first see what's the cause, all right, that have causing the overload situations to happen, and how actually we can apply the production scheme dealing with overload situations. Now let's refer these examples here for the explanation. So now suppose this is the power plant. We have three generators. These three generators is actually feeding these two loads through the bus bar as well as the transmission line. So let's say this is the stable normal system. Okay. So now what if I have additional loads added at the distribution side, and this extra load need to fit by these three generators at the power plant? So this is how does the overload conditions occurs. So during these moments of time, because extra loads, right, it will cause the frequency at the power plant start to be dropped. However, generators at the power plant are rarely troubled by overload conditions. Why? Because the total amounts of power the generators that can be produced is the functions of the prime mover. All right. So which means that this prime mover, the how much volumes of gas is being supplied is actually continuous monitors by the speed governor or the speed regulators. Okay. So now these speed regulators is actually controlling the stiff valve opening. how much gas turbine, how much gas turbine supply to it. So this volume determine these amounts of power that can be generated by these generators. Okay. However, overload situation does occur. All right. Rarely happen that it will happens. Okay. So this is why we have to apply overload protections for the generators we have. So how actually we can apply overload protection? So at the status side, we will actually implement the thermocouple, or we call it as a thermistor. It's a kind of instrument that measure the temperature's value. So we will embed it within the status winding. So right now, if we have overload conditions, so it will actually generate high heat. So this can be detected by the thermocouple seal that you have been placed at the status winding. How about for the rotor side? So for the rotor winding side, what we can do, we are not using this instrument. Instead, we will measure the resistance instead. The resistance of the first winding. Why? Because the resistance value will actually change based on temperatures. The higher the temperatures will be, the higher the resistance value will be. That's how we detect we might have overload condition for the generators. Okay, so now let's move on here to the next issue and how we can prevent it. So this time we'll talk about over voltage protections. Okay, so for over voltage situations, is occurs either as high speed transient or sustained condition at system frequency. So we know that high voltage drag is because of over speed situations, right? And it can be happen for short moments of time, or it can be sustained there for long durations at system frequency. So the reasons why we have over voltage situations is because of this, right? These three reasons here. It could be because we have defective voltage regulators. Voltage regulator we're talking about here is actually the speed governor, all right? So it might be have failures for the control. That's why there are too much things being supplied to the gas turbine that leading to overspeeding situation. So we have high voltage being drained. This is the first reasons why. And the other reasons why we have overvoltage situations is due to manual control errors. All right, due to the wrong setting, we have sudden variations of load. All right, that's why we have overvoltage. This is under transient situations. And the third reasons why we have overvoltage is because we have sudden loss of load at the distribution site due to the circuit trippings. All right, so we can use this diagram here to further explain how that this occurs. All right, how that sudden loss of loads lead to over voltage situations. Right, so we have the same situations at the power plant with only three generators that used to supply these two load at normal conditions, where the transmission line as well as the bus bar. Okay, so what happens? Let's say we have sudden loss of loads right now. All right, instead of two, I have only one load to be supplied right now. So this will actually cause the current absorbed by the load is actually reduced. So as a result, these three generators can actually rotate much more faster, leading to increments in terms of frequency. That's how does the over voltage situations occurs, right? So it's very important to take note that the generators, it has the shaft, right? That one that is rotating. It has a limited range for it to operate in terms of speed. So if the speed here increase beyond its range, it will actually cause the mechanical damage. So we have the breakdown of the generators. So how actually we can prevent generators against over voltage situations? So you can use this. The components here is the surge arrestor. So where you put it at the strategic point on the system or at the generator's terminals here. So this high voltage will actually discharge to the ground. So that's how we isolate such problems. Okay, this is the traditional way to deal with all voltage situations. All right, so now we'll start to talk about unbalanced loading conditions that could be happen for the generators. Okay, so in the event if we have balanced three-phase loads, all right, to the generator, so you connect it to the generator. So right now, the field generator, the reaction field generator is actually approximately constant, rotate in sync with the rotor field system. All right, so it will rotate at the same speed. However, if we have unbalanced three-phase fluid being supplied to the generators right now, it will cause unbalanced conditions, and these unbalanced conditions can be break down into three components. So the first component here is known as positive sequence components. So for this positive sequence component is okay. Why? Because it behaves similarly as normal situations, like let's say you're being supplied the generators with balanced load. Balanced load, which means that each phase having same magnitudes of impedance, is not different. All right. If difference is unbalanced load conditions. Okay. The other components you can file is known as negative sequence components. So for this one is a bad one. So why? Because it will create the field which is opposing to the DC field excitation circuit. So it will like create the dragging force to this excitation circuit. And the third component here is known as zero sequence component. So this is okay. Why? Because it doesn't produce any main armature reactions. So from here, whenever we have unbalanced conditions, among these three components is being we have to focus on negative sequence components. All right. Why? This is because these negative sequence components will create the reactions fields which is rotating in the same directions as the rotor system but counter to the DC field circuit. Okay. So to further understand this, let's check out this diagrams here. Now we have a gyrator. So this is the shaft. So these gyrators will actually rotate at certain speed. We call it as the rotor speed. Okay. So now, if let's say we have been looked differently, all right, with unbalanced load situation for each phase, we know that it will induce negative sequence components, right? So these negative sequence components will actually give you a speed in which it will run at the same directions as the rotor speed. All right. So under this situation, if you find the relative speed difference between the rotor as well as the status, it will become two times higher. So it will become two times of the synchronous speed. So now the resultant speed is double. All right. So with such a case, it will induce double frequency current in the field system as well as the rotor body. All right. So this is a very bad situation, which means that the gyrator is actually rotating with much higher speeds right now. All right, so now with such a case, with the frequency increase, or I should say induced is double up, all right, it will also result AD current as well. So this AD current is very proportional to the frequency. All right, so if you have much higher AD currents, which means that we have overheating situations right now for the generator. So the lifespans of the generator will actually reduce due to these situations. And this heat here, of course, can be measured as I squared R, like the copper loss here. So with such high heat, it can cause this component, the brass rotor slot here, reach to its softening point. All right, so now it's become too hot right now. So they are susceptible to being extruded under centrifugal force. So which means that it might stand above the rotor surface in the situation might have tangent strike with the status iron. All right, so with such a case, it will actually cause the damage of course to the generators. So what we can say, negative sequence components, even though with a small magnitudes, it will actually generate high heat that could damage to the generators. And this problem can be solved by implementing negative phase sequence relays or negative phase sequence components. So that's how it deals with the unbalanced loading conditions as well as its consequences here. Okay. All right, so now let's move on to discuss about the differential protection scheme where you can apply. Now is for the status winding. All right, so we can actually use this to protect against the face-to-face fault as well as face-to-ground fault as well. All right, so for this stated differential protection scheme, right, is considered as a high-speed phase fault protections, whereby it's also known as merge price circulated current scheme here. So basically, if you apply this differential protection scheme, it will give or offer the earth fault protections for some moderate impedance earth application. So what does this mean here? So let's check out these figures. So we know that for a generator, it consists of status winding for each phase. So this is phase A, B, and C. Now, this status winding is the components that I want to protect right now by using the differential protection scheme. So remember, if we are using the differentials relay, we will need to measure the entering and leaving currents to check out if there is a difference. So which indicates that I will need to implement 3 current transformer at each side of the status winding. So this 3 current transfer is measuring the entering current. This is measuring the leaving current from the status windings. Okay, so this measured current value will be fit into 3 differentials relay. So in order to detect if I have face-to-face fault, I will need to use 3 differentials relay. Okay, and take note that for the CTR for the current transformer, the current transfer ratio has to be matching with each others in order to avoid the maloperations of the differentials relay under normal situation as well as external fault situations. Now, what is the means of moderate impedance earth application? So you can see, right, for this status winding, it has been connected in Y connection. So it consists of a neutral point, right? So this neutral point of the status winding has been connected with the ground via certain elements impedance. All right, so that's how we have moderate impedance of application. So right now, if we have these connections in the situation, if we have one of the phase short circuit to ground, we are able to detect it. Why? Because there will be a upward current flowing through this neutral path right now, flow back to the source. Okay, so now let's move on here. So what if I have earth fault situations happens due to the insulation failure at the status winding? So under this situation, it will drive a severe arcing for the machine core. Where this arcing is with high energy, it can actually burn the iron at the point of fault and causing the laminations well together. So we know that for the machine core, it's not being built with one big chunk of, let's say, irons. It being made of numbers of pieces of the iron being stacked together form the lamination. So if, let's say, we have high temperatures due to the arcing jet, it will cause this laminate shock together. All right. So right now, which means that the AD currents will actually high. So with such a case, it will generate the AD current hotspot every time you turn it on. All right. So with such a case, if we have this situation, short circuit to ground for the status winding, there's a need to restack these laminations by having a proper insulation put back to each piece of irons. So this process will incur time as well as money whenever we are doing the revoke or repair of these machines. So in order to avoid this, right, so the earth fault currents has to be limited to much smaller value to a degree whereby change from rated loads current to much more lower currents value at 5 amperes. Okay, this photo is showing here where we have the burning due to the AD current hotspot, right? So this is the situations we have right now. So not only applying the differential protection scheme to pick up the earth fault situation for this status winding, the differential protection scheme, also known as merge price protection scheme, we have 2 additional protection scheme can be used as well as a backup, all right, to pick up the earth fault situations. All right, so now we use these 2 protection scheme here to limit the earth fault currents values flowing through the status winding. So the first way is known as the solidly ground system or effectively ground protection system. So whereby right now this status winding in Y connections, the neutral point will connect to the ground via low resistance wire or zero impedance wire. So under these situations is not as solidly ground system. And right now the status winding will be 100% covered against a fault situation. So it's completely protected against a fault situation. So this is the first way. The other way is by having the ground by grounding the neutral point here, where earth resistors in between. All right, and at the same time, this path we will be implemented with the current transformer together with the earth fault relay to detect if we have short circuit to ground currents right now. So in these situations, this is the protection scheme we know as a restricted earth fault protections. Why it's being named as such? This is because this time, if we are implement this way with earth resistance being placed in between the neutral point and the ground, this status warning, only part of it is being protected against a fault situation, which means that it's not 100%, only a part of it, the one that near to the neutral point here is doesn't able to be detected if we have short circuit to ground. So that's why it's known as restricted fault protection system. Okay, so now there is some problems if we implement this, the restricted earth fraud protections, right? What is the issue, right? So let's check out these diagrams here. All right, so now this is the status wording in Y connections. Now we are using a restricted earth fraud protection scheme, so which means that we will place a earth resistance in between the neutral point to the ground. So in order to detect we have fault circles, we will need to measure the current. So we use the current transfer and the reading will send to the earth fault relay. So what happens in the event if I have earth fault situations occur for the status warning near the neutral point, right? In this case here, indicate by F1, all right? So in this situation, right, the voltage, right, the phase voltage right, across due to these faults right now, actually will be very small. All right. So with such small voltage right across, the fault current flowing through here is small as well, right? So we know that there is a peak current being set to this relay to see if we have fault situations. So this more voltage will cause more current flow here. This more current might be lower than the peak current value of this fault relay. So what happens even though I have fault situations, the relay remain inoperative. It doesn't work to treat these situations, right? So now that's why we have problems right now. The fault that occurs near to the neutral point here is doesn't trip. The relay can't detect. So what if I change the fault positions, which is further away towards the ends of the status wire at this point here, labeled at F2. So this time the voltage right, the phase voltage right is actually much more bigger. So let's say here the voltage right is V2N is actually bigger than the voltage right due to the first fault near the neutral points right now. So with such high voltage value is being generated, so the fault current flowing through this part is actually much more higher. So which means that is sufficient enough to be picked up by this earth fault rate. So no issue if I have fault occurs furthest away from the neutral point. All right. And due to these reasons, only 50% up to 20% of the status wording near the neutral point here remain unprotected if we are using this scheme. That's how its names originate as restricted fault protections. All right. So practically, we will only have 85% of the status wording being protected by using this scheme. Why? Because the chance of having the earth fault situations near the neutral point is quite rare. Okay, so now let's move on to the next slide here. Now we'll see how does the chosen resistance value affect or limit the earth fault current and how actually it changed the percentage of status warning is being protected against earth fault situations. So we know that if the selected earth fault resistance value is very small, so under this situation, of course, we know that the fault current value will be very high. Why? Because resistance will try to oppose the current flow. If the resistance is small, the fault current value obviously is high. And in reverse case, if we chosen the resistance value is high instead, so now we know that the fault current value is much more lower, but it have this impact. whereby it will cost lesser percentage of the status warning is being protected, the one near to the neutral point. So how actually we can quantify this? The numbers of the percentage for the status warning doesn't being protected can be found by using this formula, whereby we have the multiplications of the earth resistance that are being chosen multiply with IOP. Here is the minimum operating currents that you measure at the primary side of the current transformer. So fault currents that could cause the operations of the relays. All right. Divided with VLN is actually the phase voltage. Okay. Then we multiply with 100% in order to get the percentage value. All right. So that's how we find or quantify the status warnings that is not being protected. Okay. So now let's look into one example here. How does the implemented restricted fault protection scheme for a specific generators? In this case, this generators is with three phase marked as R, Y, and B phase. So now what happens if I have a fault occurs on R phase, which is at this phase here, let's say, towards the ends of the stator windings due to the breakdown of the insulations to the ground. So under this situation, if you refer to this diagram, the generated phase voltage, let's say, is at 200 watts. So this 200 watt will cause a large fault current flowing through the path in such a way. So it will flow through the core, through the frames of the earth, and complete the path via the earth resistor and go back to the source right now. So it will be flow in this way. So under this situation, seeing as we have this neutral point connect with the ground via the earth resistance, so the fault currents is able to be detected if we are using the earth fault relay. So with this situation, high voltage, high fault currents, the relay will actually trip the breaker. So there's no issue if we have fault occurs here towards the ends of the status winding. So what if we shift the faulty point to point A instead? Let's say it's 50% of status winding. So 50% of 200 watt now is 100 watts right now. So the direct phase voltage now is smaller, 100 watts. Okay. So with this 100 watt is being generated, of course, it will cause the fault currents will now become much smaller. So it might be unable to be picked up by the earth fault relay. So the relay might be not able to operate if the fault is occur nearer to the neutral points right now. So with these situations, right, with the numbers value, you can see like this case here at phase R, the voltage at the end of the status warning is 200 watt, moved into half, is reduced to 100. If let's say close to neutral point, the voltage is 0 watt. So with these situations, the fault currents value will actually change, right? So now in order to ensure that most of the status warning, if we have earth fault situations, able to be picked up by this protection scheme, the earth fault relay we place here, right, the pickup current relay will try to make it as low as possible so that it can be sensitive to pick up the earth fault situations, all right? But if you have the pickup setting to be very low, this means that you might have a very sensitive of relay. So now, with such a case, we might have mal-operation in the event if we have disturbance from the power system that causing the current readings right now inaccurate, okay? Or let's say the current transfer has been saturated, of course, the reading is wrong, so it might cause mal-tripping. So we have low in terms of securities of the fault protection scheme right now in these conditions. So with such a case, in order to overcome these problems, by having a very, very low pickup setting for the fault relay that causes the mal-operations, we use bias differential relay instead. All right. So how actually is being done is by adding the restraining coil number with bias percentage at this percentage around 10 to 25% for generators protections. So for bias differential protection scheme, definitely there will be two currents being measured. All right. So one is known as differential current, the difference between entering and leaving currents. The other one will be the restraining currents or the average currents between the entering and leaving currents. Okay. So the operations for the bias differential relay will follow this curve here. All right, so that is a line, the bias line here. So if the resultant differential currents measured and flowing through the operating coil, right, and fall under these regions here, so this means that there is a true fault right now for the status wire short circuit to ground. So the relay will start to operate. Okay, so it will trip sync as this is the true fault. So in the event if I have external fault, so it causes the small currents flowing through the differential relay, let's say due to the mismatch of the two current transistors being placed at both sides of the status winding. So this time it will actually fall under these lines right now, which is the healthy regions. So it will not work. So this is same as what we have learned for transformer protections for the bias differentials relays. Alright, so what is the advantages by using a mid-price protection scheme for the gyratus protections against up fault situations? So you can see we have three advantages here. So first, it will give us the benefits of having a high speed in terms of fault isolation. So it's being recorded at 50 milliseconds of cycle time to fully isolate the fault. Besides, it also allows us to have much lower pickup setting for a fault relay. So with such a case, we can have more percentage of the status wiring near the neutral points being covered against fault situations. And the third good point of using the differential protection scheme would be we can ensure that the system complete stability. So complete stability, which means that there is no disruptions under severe true fault. Severe true fault is mean external fault situation. See, as we know that differential protection scheme should work as unique protections, right? It's only will trip if there is a fault occurs within the protected circuit. So if we have external fault, it should not work. So that is basically the advantages of the merge price protection scheme. That is the another name for differential protection scheme. Okay, so let's look into one example before I give you 5 minutes break. So we have one examples here dealing with how to find the earth resistance value for the stator wiring dealing with earth fault situation. So let's check out the examples here. So we are being given a Y connected or star connected three-phase alternators, the generators with power ratings at 10 megawatt amperes, operating at the voltage 6.6 kilowatts, and it's being protected by circulated current protection scheme. This is actually the differential protection scheme. Now the neutral point has been ground via a earth resistance with the values of R. So this time we have to find what is the value of this earth resistance if 85% of the status wiring is being protected against earth fault situation. Assume that the earth fault pickup setting is 20% of the rated current flow. Okay, so the answer is here. So now you can see we want to find the resistance value and it gives us the status wiring percentage that's being covered from earth fault pitch protections. This means that we can apply these formulas here to solve for the earth resistance value. Okay, so now this formula is allow us to find the percentage of status wiring doesn't being protected. But the questions here is the percentage of the wiring is being protected, right? So in order to find the wiring doesn't being protected against the earth fault, we will have 100% minus with 85% here. So the percentage that is not being protected is 15%. So that's how we get these solutions here. So here I have the value. So next, I will need to find what is the operating currents for the relays right now. Okay, this is to be in primary currents value. So now to find the pickup currents value at the primary side, right? All right, so we will need to find what is the rated currents values of this generator. So from there, we will actually get it by multiply the rated currents by 20%. Okay, so how can I get the rated currents for generators? I have the power, I have the voltage. Remember how we solve for the currents for the transformer is the power equations, all right? Three-phase power equation, we have power equivalent to square root of 3 VI, right? So you arrange in terms of currents, then you can find the rated current flow for this generators. So the power given here is 10 megawatt ampere. The voltage is operating at 6.6 kilowatt. This is the line voltage. So I will have the rated current at 876. So now you are ready to find what is the operating currents by multiplying the rated currents by 0.2, because 20% of rated currents as a pickup current. So it is 175 amps. So this is the current considered as the fault situations. Okay. So after you find this, I will need to find what is the phase voltage as well. So take note that for the voltage given here is actually in terms of line voltage. So to get the phase voltage, I will have line voltage divided with square root of 3 to put here. Alright, so now 6.6 kilowatt divided with square root of 3 is my phase voltage. The percentage is 50%, so it's 0.15 after dividing with 100%. Okay, bring it here, divide with 100%. So the operating current you have found as well, 175. So the earth resistance right now, the answer is 3.27 ohms. Alright, so with such a case, if you have earth resistance here at 3.27 ohms, the 50% of the status wording near the neutral port will not be protected. So that's how we solve these kinds of questions. Right, so now I will give you 5 minutes break there. I will continue the topics we have for the generator's protections.